Here we go with part 2 of the lesson. We're going to do a more complex video. We're going to do a more complex graph. Now you'll notice that now we have a fourth degree, which you haven't done before. But we're going to do the same process. I'm going to find f prime of x, because remember I'm finding the stationary points first to help me find the x-intercepts using Newton's method. So there is our derivative, and I'm solving it, and I get x equal to 0 or 3. So I've substituted Norton, and we get 1 to give the y value of the stationary point, and I substitute 3 in to the original, and I get negative 26, and so I now have the y value, so I have my stationary points. Now let's test the stationary point. So I now find the second derivative, and I'm going to substitute each of these into it. So I substitute 3, and I get a number greater than 0. So then that means a local minimum at 3, negative 26. And 0, oh dear, it gives me 0. So that means I have to test further. So I'm testing concavity now. So less than 0, if I have a number less than 0, in there, then I can substitute any number less than 0. I can substitute negative 1. I get a positive value. And if I substitute a number greater than 0 in there, but less than 3, obviously, I get a negative value. So that's the concavity. So that's what the concavity looks like. Cave up, cave down. And if we put those together, we have a point of inflection at 0 or 1. There's the y-intercept, yes. Let's put these onto a graph now. So let's put on the local minimum with a little curvy on it so that it shows where it's going, and we'll put the point of inflection, and we'll put the y-intercept. So there's the local minimum. There's the point of inflection. It's on the y-axis because note it coincides with the actual y-intercept. So there it is there. Now I need to estimate to be able to get that value there. There we have the concave up. There we have the concave down. There's the 1. So my estimates, approximately 0,7 and 4,2. On the graph sheet, on the exercises I've given you, I've given you graphs, axes to work on, and I've actually put a grid on them too to make life easier for you. So we now have our estimates. So now we can go into Newton's method. So there's the formula, and now there's the original function on top with 0,7 substituted, and there's the derivative, 4x cubed minus 12x squared below, with the estimate substituted. And that gives me an answer of 0,7, so I don't have to go any further with that one. Alright, let's do 4,2 now. Substitute that into the formula. and we end up with 4. So we're going to have to go a step further. And when we substitute 4, I haven't shown the working, and you don't really need to either. I wouldn't worry if you're sketching a graph. You could just go straight ahead and do that. So I get 4, so now I've repeated A2 and A3 are the same, so the estimate is 4. So we can now sketch the curve, and there it is. X-intercepts at 0.7 and 4 as found from Newton's method. There's our point of inflection and our minimum value there. Let's do one more like that, a similar one. In fact, it might be useful if you tried it yourself, so why don't you pause the video and try it yourself. So I'll allow a gap of about 30 seconds for you to pause the video. Okay, let's continue. Derivative. So I differentiate, solve for x, and it's 0 and -1.5. Substituting back into the original, I get -5 and about, well, approximated to -6.7. I use calculator to do all these substitutions. I hope you do the same. And what I do too, which is very useful, is don't do that substitute. Don't do that with putting -1.5 to each of those there. What I'll always do is I'll put -1.5 and then store it in memory bank A perhaps, because then I can just say recall A to the 4 plus 2 recall A cubed minus 5 equals. And I save a whole lot of keystrokes, especially when it becomes more complex. Second derivative, we're now testing the nature of these stationary points. So when I substitute -1.5, it's greater than 0, and you can see very quickly that that's the case. It doesn't take much to do it, and therefore it's a local minimum. And I substitute 0, and I get 0. So here's another point of inflection. Testing concavity again. So I take a number less than 0. So as long as it isn't, it must be close to 0 than -5, but -1 would be a convenient number because it fits that, and it's easy to substitute. You get a negative, and then we could use perhaps +1 and substitute into there, and we get a positive. So there we are, negative, so concave down, positive, so concave up. So it's a point of inflection at 0, -5. Y-intercept, 0, -5. So it's very similar to the last one, I guess. So let's slot onto the graph, because we're now going to have to find our x-intercepts. Now we need to extend that up there and that up there to see approximately where they cut the axes. There we are. So negative 2, 3, 1, 1, approximately equal to. Now I can use my Newton's method. Original function over derivative. Substituting negative 2, 3. I get negative 2, 4. So we need to substitute again. And we get negative 2, 4 back again. So then that confirms that the negative x-intercept is 2, 4. So now let's do the 1, 1. We'll do the 1, 1 and do this whole process with 1, 1. So we go back there, and we're going to substitute 1, 1 into the formula. And we get 1, 2. So we substitute again, and we get 1, 2 again. So that confirms that the correct to 1 decimal place, the x-intercept is 1, 2. And we could draw our final curve at that stage. It's going to be coming down here, turning, point of inflection, and then up there. And that's the end of the next section. So what I ask you to do now is to use the exercise sheet and do question 2 of the exercises. It's one of these types. The answers are later, the worked answers, but try to do it on your own first. If you need to look at the answers, then I do suggest you find some time a little later, a couple of days later, to try it again, because that's the best way to revise maths. If you have to look at the model answer, that's fine, but then always redo the question at least no earlier than the next day to see if you could do it on your own.